years. We are in computer cybersecurity, but my department is dealing with the technologies related to compilers. Today I will talk about PyPy project. You have heard about the PyPy project, haven't you? Raise your hands if you have not heard about it. Okay, yes, we all have heard about it. Anyway, if you do not know about PyPy, it is a program at Bitbucket. It means that people like some queer things, but on the other hand, there are some mirrors. What is PyPy? And that's my definition. PyPy is a framework, cool framework for dynamic programming languages. Dynamic language framework, and it is also a boring tutorial on this framework. They have implemented some dynamic, some language, programming languages like Python. So you can have a look at the tutorial. Anyway, it is a framework for the dynamic language. We all know, we all use Python, and I would like to show you how the Python interpreter is working. Here is a fragment of the code. It is meaningless, here is a function of a module from some PLU. If the value is more or less, we return -1. I specifically use -1 instead of -value, and I run this code in a large loop. Loop is very large indeed, a million times. At PyPy it's 1 second, and at Python it is 2 minutes and 2 seconds. It is 120 times faster. But I think the attentive viewer will see what's the reason for that. And if you are the one who knows what it is, just hold the horses. I will tell you why, what's the reason. However, had I been talking about the Python interpreter, I would say cool, it is 120 times faster, no more issues, the work is done. But the interest for me, the me, is not for that. What I am interested in is to understand why PyPy is so fast. Because it's about the GIT and the PyPy 2. And I still remember it's not 1.2, but it got faster by 3%. And they have optimized GIT. But what it means for Mr. Smith, Mr. John, it doesn't mean anything. Like we have a CPython, a regular Python, and they managed to accelerate it by means of GIT. It is some kind of props which are inside. Like we can reduce time over here, over there, and they managed to get acceleration. Is that the case or not? Is there some kind of nice idea that wraps the dynamic languages and Python among others? And it is the latter. It is the nice idea, and I would like to talk about this fine idea, because I would like to avoid using GIT buzzword, because it doesn't mean anything, and I would like everyone to understand, because the root idea is straightforward, simple. Everyone would understand it. We will have some code, but it will be quite straightforward. So what is the hype? I wanted to say why dynamic languages slow down, and I would not go into details because I might deviate strongly. And if you do not understand anything, let's discuss it at the sidelines of the meeting. But the point is that the dynamic languages are the languages that do everything. It is the code generators, and in dynamic languages everything is done in runtime. And because there is its own binding, then the dynamic typization is also implemented. And at that we have an orthogonal axis. It's related to dynamic and static typization, and it is the axis whether it is interpreted language or not, and or dynamic. And it turned out that the runtime of the dynamic languages is a thick runtime. It is binary Python that we use with Linux or any other, with Unix or any other ops system. We have a certain thing that accepts code, and when unpacking the code, this function is running on the opcodes of this code, and the code is a binary line, and those bins are analyzed, and if it is send, then adding, if 8, I will load something, something like that. That's the main loop of the CPython, and when the code is working, this code is working. This is the implementation of the processor of one of the app code. It is binary add. And so what are the things? We have a loop when it is necessary to interpret the bytecode, and there are processes that should be called. And this is the processor that adds, that sums numbers, but it does not only sum numbers, but it takes them from a stack that it is a virtual machine, and so the values are taken from the stack, they are transferred to some function which can sum Python objects at all the levels, and this function transfers control to another function and transfers the objects and the indication that those values will have to be summed, and for this thing to happen, the functionality of summing is in the type of the values, because we know that everything in Python are objects and the types are objects as well, and to sum things the summing function is in the types. It somewhere in the depth that makes it possible to sum types, and then the controls are handed over and over again and again, and it turns out that we can draw the conclusion why CPython is slow, and it works slow because we want it. It's not that we want it to be slow, but it is an intrinsic part of the design, and design is related to two basic things. We have late binding, and let me show you what it is. That's what a late binding is, because everything is looped in. Over here we have the object dot method, and everything is looked up in a runtime. This particular code would slow down, and That's what you can see in the codes when the lookup time is to be taken elsewhere. There are stranger things when people guessing that different app codes of the Python virtual machine load fast and the other one have different performance. They work in the following manner. They would like to have more value as a local transient, but they use it as a default value into the signature, and because the code would assume another view, there will be a different code that will be reading it from the other time. And if you see this code, then it's not realistic. Then there's another problem, like boxing. We do not have pressed for time, and there is a basic structure in the CPython interpreter, and this subject, like everything is object, is in Python is derived from over here, and like this is the representation of the number 100, which is has been read from the CPython. It is 352 bits, and the color green shows where the number 100 is located, and we cannot do without it. So could we get rid of the virtual machine overheads? Python is Python, and we cannot do anything about it. Some is saying that we have the Python, could we get rid of it? And Michael is saying that we cannot, but I insist that we can, and we can do that without any hubs. So that's what's the point? We have a Python program, and this Python program rules the interpreter, and it works as if it were an interpreter. And if we will interpret this problem philosophically, the dynamism, the vagueness is inbuilt in the different codes, in the code inside the interpreter, because it is a stack machine, and there are different stacks over there. At that, part of the vagueness that is inside the user code is maps on the vagueness of the code inside the virtual machines. If we manage to merge those in the runtime, or combine those in the runtime, at this particular moment it is this final result delivery will not be an interpreter of the Python, but it will do some work, and in this case we will manage somewhat to get rid of the vagueness in the machine and in the code. So that's the task, and that's the idea that I've been playing with, and that's how it was implemented in practice. Here is abs function, and returning again and again, and that's its a representation of the abs function. And of course one cannot see it in the runtime. It is the user program, and here is a bulky slide, but it's not that cumbersome at all. It is something that is written in Python. It is a main loop of the interpreter, and what we do over here, we get a frame. Here is it. We have some local transients, because it's a stacked machine. We have a code counter to know what instruction we execute, and then the interpretation takes place in those loops, and we see that if over here it is load const. it means that we should upload a certain value in which was compiled into the code. When this is done, when we enter a certain value into the stack, then we forward the code counter further, and we return into the loop. That's how it works. That's why it's const, and something is being pushed onto the stack. The only thing that this particular function, it takes it from other, or like over here. How do we build multiply? We'll binary multiply. We took values from stack. We put it into the function do multiplication, and the model is pretty straightforward. And within this particular model, and using this code, the question is, could we possibly combine those? So a question, here is this presentation code and this one. Do you think we can get rid of both, but at the same time retain the computability of this function, at least for some of the values? Any ideas how we can approach this challenge, this code and this one? Okay, I won't torture you. So what if instead of all those loop, we... Yeah, by the way, yes, another piece of information. This is an important thing, and you shouldn't forget about it as well, because in the sandbox we also model the fact that the values are wrapped in the box. Like remember that 100 inside the object is a small thing, and we have a lot of boxes like that, and inside those boxes we have genuine values, but the interpreter cannot control those. That's why the objects are like that, long object and etc. The other things which are on the screen, and but we cannot directly manipulate. Just imagine that it is a C level. We cannot sum two structs. That's why we should use the specific functions that make the adding or summing, like a long object 10 and long object 20, and they will return us 30. They cannot just return us 30, but it's nonsense from the point of view of interpreter. So can we merge the code and the code of the virtual machine? What if we just take the code that we had, and because we know what code we want to implement, and we put the implementation of each codes inside. Of course we will have the stack and all those things, but we will get rid of the counter, because there is no separate essence, because the program is part of this code, but stack still remains. And let's look attentively at this code. The stack is there, but what we do with it is nonsense, because we add something and then we get it away, like adding and taking away. We do some strange work, but this code is valid semantically. And what if we just delete, get rid of those pairs of add and subtract? So we got rid of those, and that's what is left. We have the transient function, and remember, that's the code that we implement, and it is this code that we implement, and It should calculate the number, and it means that we have the comparison with 0, and that's what we are doing. We deal with the comparator function, and we put the dynamic value from frame and another constant value from the code.
Could we get rid of it somehow? This slide serves to demonstrate that it's possible to do without comparator's function, because in this case we dynamically take it away. Here you can see comparator 5, and this is just a designation for it. Well, we can get rid of this comparator because we know this information by now. And then we can see that even within this simple function we use a wrapped value. There's something I wanted to show you. The main thing here is not to get confused. You understand that we get rid of increasingly large number of things, just of the dynamic essence of the language. Here we can see that we calculate compare result. We know that by design this function should return full object, but we know that after that we get a low-level value from it. And we also know that this long object does not leave the function. That's why we do not need to calculate it. We only need to calculate the long-level value in there. Then we have functions such as do multiplication, which calculates multiplication, and then we can see functions gt2, and we can look at the implementation, because normally if you look at CPython you will see that those functions by object or number or gt or lt, whatever they call them, they have something like if an element number 1 has in or element 2 has something like that, you should do something as follows. And here do multiplication does the same thing. We use two values. If the types of these values are ints, then it does native multiplications and calculates them and puts them somewhere and creates a new long object, and the same applies to long queue. So first we get the values and then we get the long object. If we know in advance that we are to calculate a specific function, for instance ABC from -20, it means that the whole of this overhead here, various checks, etc., are not required if we already know that we are based on long object, which is negative. And finally, here we get rid of the functions themselves. When I say get rid of, we take them away. And here we have bool object, that is to say the result of the compare function, and then a long object as a result of multiplication by the native value. In the past it was wrapped, and now it is a native value. And then we can see here CMP result, and then we take it away, but it doesn't make any sense because we can directly use this value. Then we look at this thing, and possibly we cannot do anything about this code anymore. But what if it is not like that? Here it says if a certain value is over 0, then we return the value itself. If it is lower than 0, then we multiply it by -1. But if we know already that it is below 0, then, as you understand, each one of these simplifications is tuned even better for the prime time. So we keep tuning into it. So this is a code which will assume -20 and the frame, and it will use -1 and low-level value. So it is quite a fast code. What should follow then if we keep having -20 started continuously? Could we advance anymore? What if we just calculate absorbed -20 and do some mini check at the very beginning to arrive at cached value? So in this case, this would be just instantaneous. What could we advance even further on? It would be quite a scoop to have it like this without any code at all. And it so happens that it does occur. This is in the example when the speed was 120 times higher. This is what happened. The compiler, and not even the compiler, but I would say rather the internal structure of PyPy. I don't want to go into any detail. If any of you are interested, I could elaborate it just on the sidewalks. It means that this code could be optimized just like the guys from the Haskell community joke quite often. And finally, we arrive at a situation when practically nothing is left of the function. It may happen that nothing absolutely would be left. I also wanted to show you something else, but I would like now to try and answer some of your questions, if you have any by now. So the idea is that PyPy is based on dynamic languages which are too slow for programming. Performance can be achieved, but not through the methods used in language compiling. It is done through optimization in runtime. We should understand what we run, and only then we would be able to refine it. That's the way it is. Thank you for your attention. Are there any questions? If any. Well, incidentally, if any of you would like to play with PyPy, you would see that. Yes, please. Any questions? Hello. I'm Semyon. My question is as follows. I believe that most of those present here know the answer, but I think you should mention it here. If everything is so cool, why is it still alive, and why isn't everybody not using PyPy now? Well, my question would be, why aren't they using, are they still using Python 2 if we have Python 3 now? We are all human. So what could we require of people? The trick is that the compatibility between PyPy and CPy, even at the level of Python code, there are certain contradictions and differences in interpretations. However, basically they are well compatible. For instance, you have heaps of Python codes. If something doesn't work, you use PyPy instead of Python, and you may then wait and see whether it works. If it is faster now, then it's okay. it would be just a drop-in replacement and you can use it. Thank you. So, any more questions? Yes, please. Is there a question? I just wanted to add something. It's quite an interesting subject because what happens is that PyPy is fast because of GIT, but there is no such thing as GIT in PyPy. Nobody ever wrote GIT in PyPy, so it's an illusion that GIT is based on Python's concept of PyPy. It is generated as a virtual machine based on Python. We should be well aware of it, and it takes some time to understand it. You should read the PhD doctorates, and this is really quite a good technology. I just wanted to ask you something. It means that the first generation of bytecode takes longer than based on Python. And my second question, if we have def random, then we won't have any optimization. Is that correct? Well, clearly, refining the code takes a lot of levels to pass through. If you have issue random, we would have a number of bytes or something that is not quite clear. But say we get a sequence of numbers, say 0, etc., whole numbers and fraction numbers and fractions. I don't want to use the word GIT because it's not quite clear. However, there is a GIT there which would quickly understand that we are using this code in the context of numbers with whole numbers or with a floating point, and it will soon understand which function we have and what we do inside the function, and the code would be refined very fast to use the floats which are more than 6 and in between 10 and 100, and it would work as a machine code. But then my question is again, could it be then more advantageous to do sorting sometimes first and then run it? For instance, if we have fault and some other confusing things, well, this is a good question. If we input to a function just a mixture of various types, one of the coolest types of optimizations, which is called polymorphous flying cache, then it would stop working. It means if there are a number of contradictory instructions input, and then it says jump there or jump here, and if the number of those types is higher than a certain value, the long line cache is not created. Then this problem could arise, and this optimization would be disabled. However, the other optimizations will be there. Yes, please. Good afternoon. I have a question as follows. For instance, I have never heard anything about PyPy. I have come here for the first time in my life, and here I learned that it is not an interpreter but team word for dynamic languages. Could I theoretically apply PyPy for PHP or Ruby? Yes, you can. When I say framework, I mean it. I mean it is framework. But how can I do it? Just in a nutshell. Just as we have just discussed, inside PyPy there is a Python interpreter which is called PyPy. But basically inside the project is a framework for writing programming languages. That's why PyPy, as an interpreter, uses it. That's why I said that it is just a long-standing tutorial for the languages. So if I want to use PyPHT, I can do it. You may use this framework, understand how PHP works, read various details of programming, but you use this framework, and there are heaps of various facilities there as to how to interpret it, etc. So you pack it up with all kinds of things, and then you get a PHP interpreter, and it is already there on that framework. And we also have Ruby's implementation there, and Prolog implementation, and the implementation of tens of other things, just heaps of them. So it is really a framework ready to use. I do understand that this is quite a niche subject matter for those of you who write languages. It so happens that I have been writing languages, that's what I think about it. Thank you for your attention.